Hello. The purpose of this video today is to talk about calculating the pH of a salt solution. When we talk about classifying salt solutions as acidic, basic, or neutral, and hence determining their pH, there are a couple things to keep in mind. First, remember that when you place that salt in water, it's going to produce cations and anions. So we've got to consider the properties of both when we're talking about the acid and base properties of the salt solution. Specifically, we want to know if the anion is basic or neutral, and if the cation is acidic or neutral. If both ions, the cation and anion, have acidic and basic properties, then you actually have to turn to the Ka and Kb of their conjugates to make the decision about which is stronger. The larger K value, of course, being the winner. This is probably best illustrated by looking at an example. So today, the example that we'll use is 0.25 molar sodium acetate at 25 degrees Celsius. And the question is, what's the pH of the solution? We also want to use that pH to validate our prediction of whether the solution will be acidic or basic. To make that prediction about the acid or base properties of this salt, we need to talk about the ions that are produced when you put sodium acetate in water. Those two ions are Na plus and C2H3O2 minus, or the acetate ion. Sodium ions probably can be thought of as a result of sodium hydroxide. And sodium hydroxide is a very strong base, which leaves the sodium ions as a really, really, really weak acid. So weak that it cannot interact with water, and therefore in this scenario will not affect the pH of the solution. These type of cations we call neutral cations. So the sodium ion is not going to have any impact on what we do going forward. The acetate anion, on the other hand, probably originated as acetic acid. And acetic acid is a weak acid. According to conjugate acid-base theory, that makes the acetate ion a reasonably strong base, at least strong enough that it can interact with water, which means it probably will affect the pH of our solution. And because it's an anion, when it interacts with water, it will remove a proton, leaving behind hydroxide ions. And therefore, we expect this anion to produce a basic solution. So based on this assessment, we predict the pH that we're about to calculate is going to be greater than 7. The first step in determining the actual pH is going to be writing the reaction that occurs here. So specifically, we're going to look at the reaction of the acetate ion and water. And that reaction will produce acetic acid, C2H3O2, and it will leave behind and also produce some hydroxide ions. As I pointed out earlier, and you can clearly see now, this is a reaction where the acetate ion is acting as a base. In other words, this particular reaction has a Kb expression associated with it. The challenge here is that we don't know the Kb value for the acetate ion. You can't go to the literature and find it. But we can go to the literature and find the Ka value for acetic acid. The good news is it's pretty easy to calculate the Kb if you have a Ka. The Kb is simply going to be equal to the Kw divided by Ka. And at 25 degrees Celsius, Kw is 1 times 10 to the minus 14. And if you go to the literature and look up the value for acetic acid, the Ka value, you will find that it is 1.8 times 10 to the minus 5. If you perform this calculation, the Kb is 5.6 times 10 to the minus 10. And the Kb expression for this reaction is the concentration of acetic acid times the concentration of the hydroxide ion divided by the concentration of that acetate ion. Now that we are armed with this information, we are ready to construct our ice table for our reaction. In this case, we have limited amount of information we can fill in our ice table, and it all comes in the initial row. The initial concentration of the acetate ion, 0.250 molar, and the initial concentration of acetic acid and hydroxide ions are each 0. We don't have any other information at this point to help us determine equilibrium concentrations, so we are going to need to plug in X's. So for the change in concentration of both the hydroxide ion and the acetic acid, we will plug in plus X. And because the stoichiometry remains 1-to-1, for the change in concentration of the acetate ion, we will plug in minus X. Minus, of course, because it's a reactant versus a product in this scenario. Which means at equilibrium, we have 0.250 minus X for the acetate ion, X for the concentration of acetic acid, and X for the concentration of hydroxide ions. That's an important note here. When we solve for X in a moment, we're going to have the concentration of hydroxide ions. A common mistake in this problem is forgetting what X represents. So let's keep that in mind as we move forward. Okay? If you plug this into the Kb expression, we end up with an expression that is 5.6 times 10 to the minus 10 equaling X squared over 0.250 minus X. If we tried to solve this right now, it would be a quadratic, but there is good news. Look at the size of Kb. It's 10 to the minus 10. It's really small. So using an X is small approximation here is perfectly valid. And so if you do that, our work simplifies to 5.6 times 10 to the minus 10 equals X squared over 0.250. And if you solve this, you're going to get X equaling the square root of 1.4 times 10 to the minus 10, which is equal to 1.2 times 10 to the minus 5 molar. So we have our value of X, and allow me to switch slides here so we have a little more space. But now what we need to do is figure out what does that value of X tell us about the pH. Recall that X, which is 1.2 times 10 to the minus 5 molar, based on our ice table, is equal to the concentration of OH minus. Which means if we take the negative log of that value, or the negative log of 1.2 times 10 to the minus 5, what we will actually get is the pOH. And if you plug that into your calculator, you'll get a pOH equal to 4.93. 4.93. The pH is equal to 14.00 minus the pOH, or 14.00 minus 4.93, which means the pH of this solution is 9.07, or slightly basic as we originally predicted. I hope this video has helped you understand a little bit about how to classify salt solutions and how to determine their pH.